Namaste children. In this class we discuss unit number 3 fluid. Already I told you what is called fluid. Gases and liquids are called fluid. So in this chapter we are going to see atmospheric pressure and measurement of atmospheric pressure. So what is called atmospheric pressure? The earth is surrounded by a certain layer of air nearly up to 300 kilometers. So this layer of air is called earth atmosphere. This layer of air is called earth atmosphere. So you know very well, in previous video you learned that the pressure is exerted on the earth. So this layer of air is exerted, certain air pressure is called atmospheric pressure. This atmospheric pressure is determined by the instrument called barometer, which is designed by the German physicist Torricelli. Okay, for our better understanding purpose, I give some animated video. Okay, let us see the video.
We are surrounded by air from all the directions. This envelope of air around us is what we call atmosphere. Does air also exert pressure on objects on the earth? In our previous video, we studied that the liquid exerts pressure in all directions. For example, here we have the water in a beaker. Due to gravity, this water is pulled down towards the earth. If we divide this water into different layers, then each layer is being pulled down by the earth. Due to this pull, water exerts downward pressure and this pressure is uneven throughout. That is, the bottom layer experiences more pressure than the top layer. This is because the weight of water above the bottom layer is more, and the pressure decreases as we go upwards. In fact, we saw that the water exerts pressure in all directions and not only in the downward direction. One more thing that we studied about the liquid pressure is that at any point in a liquid, the pressure is the same in all directions. That is, if I take any point here in this water, the pressure exerted by water here is the same in all the directions. Air also behaves in the same way. Just like water, air is also being pulled down by the Earth's gravitational force. This force applies pressure on the air in the downward direction. The pressure exerted by air is called air pressure or atmospheric pressure. Did you know that the atmosphere is divided into different layers? The atmosphere is divided into 5 layers, namely the troposphere, stratosphere, mesosphere, thermosphere and exosphere. The pressure in the troposphere, which is the bottommost layer, is higher than the pressure in the layers above it. And I'm sure you can guess the reason why. This is because the weight of the air above the troposphere is greater than the weight of the air above, say, the stratosphere. The air pressure also acts in every direction and not only in the downward direction. And finally, just like the pressure in liquids, the air pressure at a particular height above the Earth's surface is same in all directions. That is, if I take these 2 points at the same distance above the Earth's surface, then the air at this point will exert an equal pressure in all the directions, just like the air at this point. Let's look at an interesting graph now. A graph which represents pressure at a particular altitude. The graph also represents how the pressure varies from layer to layer. The troposphere layer is closest to the surface of the Earth and the pressure in this layer goes up to 100,000 Pascal, where Pascals, represented by Pa, is the SI unit of pressure. This is massive pressure. This pressure pushes and pulls the object on the surface on the Earth. For example, If I take a table with the upper surface of 1 by 1 meter, the pressure exerted by the air on the table in the downward direction is greater than 1 lakh pascals. This is equivalent to 10 cars being put on this table. Yes, 10 cars. I know what you must be thinking. Why doesn't this surface collapse under this huge pressure? How does it handle such massive pressure acting down on it? A little while ago, we said that the pressure exerted at points above the Earth's surface is equal in all directions. So the pressure at every point on the table is the same in all the directions. That is, if downward pressure is pushing the table surface with a great force, then the upward pressure is also pushing it in the upward direction with the same force. Both the forces are balanced and the table does not collapse. As I said, pressure is not only acting in these two directions, it is acting on the surface in all the directions. Pressures acting in opposite directions cancel each other out. Here is one cool experiment that you can also perform at home. Take a plastic bottle filled with water. Take a cardboard paper and place it on the open end of the bottle like this. Hold this paper with your hand so that it does not move from its position and invert the bottle. Now let go of the paper. What did you see? The cardboard paper sticks to the surface. Why is it held to the surface? It is held to the surface because of the air pressure that is pushing the paper in the upward direction. The upward air pressure is sufficient to counter the downward push exerted by the water. Now make few holes in the bottle at its base. What happens now? Why did the paper fall off? Did the upward pressure on it stop acting or did it reduce in the value? No, it didn't. The upward pressure on it by the air remains the same, but the downward pressure increased in its value. When we made holes in the bottle, we allowed air to flow inside it from the top. The air from the top started exerting pressure on the water. The combined pressure of water and air from top could easily overcome the pressure exerted by air from the bottom. Hence, there is net force acting on the paper in the downward direction. That is, there is more pressure in the downward direction. That is the reason why this paper gets detached from the surface.
Well, my dear children, before you going to know about how the barometer works, you must know the principle of barometer. The barometer works by balancing the mercury in the glass tube against the outside air pressure. If the air pressure increases, it pushes more of the mercury up into the tube, and if the air pressure decreases, more of the mercury drains from the tube. Okay? So this is the principle of barometer. Now let you see the video how the barometer works. Okay?
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Well, my dear children, I hope you understood well all the concepts related to the atmospheric pressure and barometer. Barometer is one of the important 5-mark question for our examination point of view. So, read wisely with the help of your textbook and you make it note in your physics notebook. Okay, I hope once again you understood well. Thank you. Bye.